Let's go. Today's world relies on the principles of secure communication. Whether it's sending a message to a friend or paying for your weekly groceries, cryptography assures that your data cannot be read by anyone than those precious few. However, quantum computers, an unrelated topic at first glance, could end this line of thinking. Although not currently a threat, the mere premise of their existence in the future jeopardizes information security today. Thankfully, not all hope is lost, with new cryptographic methods possibly mitigating this threat. Statistically, you've probably never even heard of these newfangled quantum computers, or at least unaware of its impacts, so feel free to join me down this rabbit hole. On your way down, we will explore what cryptography and quantum computers are, how quantum computers threaten cryptography, and what can be done to stop it. But first, let's learn to walk before we run. Research suggests that quantum computers rely on quantum superposition and entanglement, which are two fundamental principles of quantum mechanics. Described by cybersecurity scientist Vasilios Mavroides as the field related to microscopic physical phenomena and their strange behavior. Classical computers, like the device you're using to watch this right now, utilizes binary information storage, where ones and zeros allow modification and representation of information in bits. According to the National Academies of Sciences, Engineering and Medicine, quantum computers instead utilize qubits, which do not adhere to the determinable state of classical systems, instead existing in multiple states all at once. A further study conducted by Mavroides states that this allows qubits to exist not only in the 0 or 1 state, but in both simultaneously, which is called a superposition, at least until they are expected, where it collapses, allowing only one state to be observed. However, while in the superpositions, any operations performed on the qubits will be performed on every superposition. As revealed by Kirsch, a 1-qubit computer is not particularly useful, only being able to exist in 2 states at once. However, through entanglement, qubits can be linked in such a way that the states rely on each other, effectively providing a single system that simultaneously represents 2 to the power of n states given n qubits. Into the realm of less confusing concepts, Quadir's a review paper on cryptography defines encryption as techniques that cipher data, that make the data unreadable to the human eye unless decrypted by algorithms that are predefined by the sender. For the everyday person like you and me, encryption is a must-have, as it is built into almost all types of electronic information transfer, allowing everything from private messaging to bank transfers to have undebated security. By far, the most popular algorithm is known as RSA, which utilizes asymmetric encryption and bases itself off having a public key used to make data unreadable and a private key used to make it readable again. Multiple sources state that RSA encryption is based on the practical impossibility of factorizing a semiprime, a multiple of 2 prime numbers, into its original prime counterparts.
For example, let's say that Bob would like to send an encrypted message to Alice. First, Alice's computer will pick 2 prime numbers. These will be kept private by Alice, called the private key. By multiplying these 2 together, Alice obtains the semi-prime public key. Think of the public key as a padlock, with the private key as the key. Bob takes his message and encrypts it using the public key, analogous to locking his message with a padlock. Alice can then use her private key to decrypt it by unlocking the padlock, returning it back to a readable state. Since the factors of the semi-prime are the only thing that can be used to decrypt the message, and only Alice knows the factors, only Alice can decrypt the message.
Due to the difficulty of factorizing these semiprimes, current research suggests that today, RSA cannot be broken, as utilizing even the best-known algorithm and a supercomputer would take 16 million years to perform this factorization. However, when exploring the impacts of quantum computers, many sources included mention of Shor's algorithm, which would make it possible to compute the secret key of RSA encryption. Since the secrecy of the secret key is foundational to RSA, any algorithm that can calculate the secret key, such as Shor's algorithm, poses a massive threat to today's cryptography.
Shor's algorithm was first developed by mathematician Peter Shor, and according to Kirsch, allows an RSA semiprime to be factored in the same amount of time that a classical computer can multiply the prime factors together. Considering the lock and key analogy from earlier, Shor's algorithm equates to a third party being able to reverse engineer the key for any lock, purely based off the design of the lock. Thus, this allows anyone who can implement Shor's algorithm to effectively break RSA encryption through the following steps. Let n be the semiprime of p and q. N is the public key, while P and Q are the private key. First, guess a number less than n. The second step here most likely involves utilizing Euclid's algorithm to ensure that the factor has not been found by calculating the greatest common denominator, however some sources did skip this step. Third, due to a property of primes, multiplying the prime by itself enough times will result in a multiple of n plus 1. Therefore, by taking the modulus of g to the power of r enough times, eventually a remainder of 1 will be found. The exponent of g that resulted in remainder 1 will be substituted for r. Fourth, the original equation can then be rearranged to show that g to the power of r take 1 is equal to m times n, which can be factorized through a differentiation of two squares to form g to the power of r on 2 take 1 times g to the power of r on 2 plus 1 is equal to m times n. Since we know that the right-hand side contains p and q as factors of n, it can be said that the left-hand side also contains p and q as factors as well. From here, we can simply use Euclid's algorithm to find the greatest common denominator between g to the power of r on 2 plus or minus 1 and n, therefore resulting in a divisor of n that is likely to be p or q. Given either of these, it is trivial to find the other, but if we already know the algorithm, then where do quantum computers even get involved?
According to physics PhD Derek Muller, it is the third step in this process that takes unfeasibly long on classical computers. Due to the large prime numbers used by RSA resulting in many modulus calculations required to find a remainder of 1. Instead, according to both Muller and an overview of quantum cryptography in Shor's algorithm, quantum computers can significantly speed up this process. Hence, only when utilized in conjunction with quantum computers does Shor's algorithm propose a real threat to cryptography.
First, split the qubits into two sets. One with a superposition containing every number from 0 to 10 to the power of 1234, and another entangled set that only contains zeros. Then raise g to the power of the first set, divide everything in that set by n, and store the remainders in the second set. The remainder superposition can then be measured to obtain a random remainder and collapse the state of the first set into only the values of g to the power of r that resulted in the same remainders. Since the remainders are periodic, the value of r can thus be found by utilizing a quantum Fourier transform to determine the periodicity of the first set, hence resulting in r.
According to an interview with Dr. Dongxi Lao, CSIRO's cybersecurity and quantum systems team leader, the conjunction of quantum computers and Shor's algorithm allows RSA private keys to be found from public keys. Since the secrecy of private keys are fundamental to RSA encrypted data remaining encrypted, a massive cryptographic threat is proposed through nullification of the most widely used cryptographic algorithm. However, not all hope is lost, as there is always light at the end of the tunnel. In 2016, the National Institute of Standards and Technologies, also known as NIST, recognized the cryptographic threat proposed by Shor's algorithm, stating that if large-scale quantum computers are ever built, they will compromise the security of many commonly used cryptographic algorithms. To mitigate this, they developed standards of post-quantum cryptography by soliciting post-quantum cryptosystems from the public, and evaluating them to form standards in a post-quantum world. According to both Muller and NIST, 4 algorithms were selected for the standard: Crystals Kyber, Crystals Lithium, Falcon, and Sphinx Plus. Out of these 4, 3 are based on lattices rather than primes, utilizing problems known as lattice-based problems. That is to quantum computers what prime factorization is to classical computers. But how does it work? Since it bases itself on vectors and lattices rather than primes, lattice-based cryptography such as Crystals Kyber mitigates the threats posed by quantum computers and Shor's algorithm. According to both Muller and mathematics PhD Kelsey Houston Edwards, lattice-based cryptography is based on the problem of finding the shortest vector to a point on a lattice. Now I know that's a lot, but hold on. Both explanations given by Muller and Houston Edwards concurred on the following.
First, think about two arrows. Call them V1 and V2, the good set. Each of these arrows has an x component, moving in the horizontal direction, and a y component, which moves in the vertical direction, and as such can be called vectors. By stringing these vectors in chains, we can find points reachable by these two vectors, which reveals a repeating pattern that is described by these vectors, called the lattice of these vectors. However, more vectors are possible on this lattice, each of which can be derived from the original vectors, however are more complicated. We'll call these B1 and B2, the bad set. While they can still reach every point on the lattice, the chain of vectors required to do so is significantly more complicated, with the difficulty increasing the closer to parallel these vectors become. To explain how this relates to cryptography, let's return to Alice and Bob. Alice first generates a set of good vectors, which she keeps private, as the private key, and then derives a set of bad vectors, which she publishes as the public key. To send a message to Alice, Bob uses the bad vectors to pick a point on the lattice that corresponds to his message and adds some random noise to it. Bob can then send the noisy point's position back to Alice. Since Alice has the private key, she can easily generate the entire lattice and find the closest point, thus decrypting the message. However, a third party would have a significantly more difficult time, as they can only use the published bad set of vectors. Even if they use the vectors to find a point that is close, they will have to find all points around this to ensure that there aren't any lattice points closer. Thus, it is practically impossible for the eavesdropper to find the closest point on the lattice and decrypt the message and break the encryption, while Alice can do it easily.
On a 2D plane, this is trivial, even for a classical computer. However, it becomes a lot more difficult with increasing dimensions, as the number of vectors involved increases the computational power required to practically impossible levels. With the proposed approximately 1,000 dimension lattice, as indicated by Muller, taking one step in the right direction on one of those directions, and you could potentially be taking a wrong step in the other 999. With the sheer scale of this encryption scheme, it's easy to see how we could mitigate the threat of quantum computers. However, every solution has its downsides. While NIST states that they are working with companies to attempt implementation of these new cryptographic algorithms into future technologies by providing systematic approaches for migrating from vulnerable algorithms, the interview with Dr. Lau revealed some potential issues. He countered that switching algorithms could be challenging for several reasons. These include the differing performance between algorithms, the lack of tools to help companies switch, and the sheer variety of equipment that must be modified for compliance with quantum-resistant cryptographic technologies. Essentially, while post-quantum resistant encryption already exists, there are still several challenges that prevent its implementation. Today, encryption bases itself upon prime number factorization, with one of the largest cryptographic algorithms, RSA, using this method to secure many forms of electronic communication used by humanity every day. Tomorrow, encryption could base itself upon lattice problems to mitigate the impacts of quantum computers. Thanks to their unique ability to exist in multiple states at once, quantum computers can utilize Shor's algorithm to effectively nullify the encryption provided by modern algorithms, possibly exposing encrypted data to anyone. However, even NIST proposed solutions are not foolproof, as the implementation of new algorithms such as Crystal's Kyber could be held back by its technical differences to RSA. Evidently, quantum computers pose a massive threat to cryptography, through their ability to implement Shor's algorithm and undermine the most common cryptographic algorithm. This could expose much of the data meant to be kept secret on the internet. However, alternate cryptographic algorithms have already been developed to help mitigate this threat. And with that, it's dark, I've seen the view, my sports is done, and it's time to go home.